Machine learning is one of the top technologies of the 21st century. It has brought in a revolution in the business sectors. Hello everyone. Welcome to this full course video on machine learning. This video will help you understand all the concepts and give you ample hands-on experience building machine learning models. We have our experienced instructors who will take you through this course. First, you will learn the basics of machine learning and jump into understanding the various machine learning algorithms. You will learn about linear regression, logistic regression, decision trees, support vector machines, and many more. Then, you will look at reinforcement learning and understand mathematics for machine learning. You will learn the concepts such as principal component analysis, regularization, and feature selection. Finally, you will perform US election prediction analysis and understand the machine learning roadmap for 2021. So let's begin with a short animated video on machine learning.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify Song A. But when the choice became complicated, as in the case of Song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for Song B, if we draw a circle around the Song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of Song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro, and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams, and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with the respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are two clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these two clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as our final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody is online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have largely increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please, I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks!
No problem.
Comment below some interesting everyday examples around you where machines are learning and doing amazing jobs. So that's all for machine learning basics today from my side.
What is machine learning? Hello, my name is Richard Kirshner. I'm with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Today we're covering what is machine learning. What's in it for you? We're going to cover the basics of machine learning. What is machine learning? Artificial intelligence versus machine learning versus deep learning. How does machine learning work? Types of machine learning prerequisites, applications of machine learning. Here we have our, it looks a little bit like Frankenstein, our Frankenstein-looking robot. Today, let me tell you what is machine learning. Machine learning works on the development of computer programs that can access data and use it to automatically learn and improve from experience. Watch a robot builder construct a house in 2 days. This was back in July 29th, 2016, so that's pretty impressive. This amount of time to continue to grow in its development. And it's smart enough to leave spaces in the brickwork for wiring and plumbing and can even cut and shape bricks to size. Amazon Echo relies on machine learning, and with more data it becomes more accurate. Play your favorite music, order pizza from Domino's, voice control your home, request rides from Uber. Have you ever wondered the difference between AI, machine learning, and deep learning? Artificial intelligence, a technique which enables machines to mimic human behavior. This is really important because this is how we are able to gauge how well our computations or what we're working on works, is the fact that we're mimicking human behavior. We're using this to replace human work and make it more efficient and make it more streamlined and more accurate. And so the center of artificial intelligence is the big picture of all of this put together. IBM Deep Blue Chess, electronic game characters. Those are just a couple examples of artificial intelligence. Machine learning, a technique which uses statistical methods enabling machines to learn from their past data. So this means if you have your input from last time and you have your answer, you use that to help prove the next guess it makes for the correct answer. IBM Watson, Google search algorithm, email spam filters, these are all part of machine learning. And then deep learning, which is a subset of machine learning, composing algorithms that allow a model to train itself and perform tasks. AlphaGo, natural speech recognition. These are a couple examples. Deep learning is associated with tools like neural networks where it's kind of a black box. As it learns, it changes all these things that are, as a human, we would have a very hard time tracking. And it's able to come up with an answer from that. Now let's see how machine learning works. First, we start with training the data. Once we've trained the data, we go into the machine learning algorithm, which then puts the data into a processing, which then goes down to another machine learning algorithm. And then we take new data, because you have to test whatever you did and make sure it works correctly, and we put that into the same algorithm. Once we do that, we check our prediction, we check our results, and from the prediction, if we've set aside some training data and we find out it didn't do a good job predicting it, and it gets a thumbs down as you see, then we go back to the beginning and we retrain the algorithm. And a lot of times it's not just about getting the wrong answer, it's about continually trying to get a better answer. So you'll see the first time you might be like, oh, this is not the answer I want, depending on what domain you're working in, whether it's medical, economical, business, stocks, whatever. You try out your model, and if it's not giving you a good answer, you retrain it. If you think you can get a better answer, you retrain it, and you keep doing that until you get the best answer you can. Let's see the types of machine learning. Supervised learning, unsupervised learning. There's a number of ways to divide up machine learning and how it works. These are two main categories you can divide it into. Supervised learning, we have a known amount of data. So in this case, we have a bunch of apples. We have a machine learning algorithm. It goes through the process. It goes through and trains a model based on that known data. And then once you've trained your model on the known stuff, you can then put an unknown data in there and you get a new response. And of course, in this particular one, it's an apple. So it's trying to figure out whether it's an apple or another fruit. There are many different algorithms you can use for computing this information, for doing this supervised training. Just to list some of the top ones that are currently being used, and by no means there's more than just this. So by no means this isn't the complete list. There's polynomial regression, there's a random forest, there's linear regression, there's logistic regression, there's decision trees, there's k-nearest neighbors, and there's naive Bayes. Like I said, this is just a short list of some of the many tools that are out there nowadays. And if you have supervised learning, then we should also look at unsupervised learning. Unsupervised learning. So we have unknown data. In this case, you can see we have a bunch of fruit, and we might not have labeled it. We don't know. We've never had anybody look at it and say, this is what this is. And we take that data, and we put it through the machine learning algorithm. And then that goes through the processing, and then the trained model. And what the trained model says, hey, can I see a pattern here? And from that pattern, it divides it up into a response, in this case, apples and pears. You can see some of these things look just like the other, and it tries to put them all together so that you get similar things in similar groups. And again, we have a nice list of algorithms here, and this is not the only algorithms used for this. So don't limit yourself to just these. These are just some of the primary ones used today. And of course, we have the k-means clustering, singular value decomposition, fuzzy means, partial least squares, a priori, hierarchical clustering, principal component analysis. Machine learning prerequisites. Computer science, fundamentals and programming. So any of the machine learning out today, you have to know some basic scripting or programming. Intermediate statistical knowledge. You have to understand a little bit about probabilities. If A is current, how likely is B going to happen? If there's clouds overhead, how likely is it going to rain? Linear algebra and intermediate calculus. The linear algebra is very important because you have to understand basically drawing a line through the data points and what that means. That's the most fundamental linear regression models. You draw a line through all your data and you use that line to compute new values. Intermediate calculus means you need to have a little bit of understanding of what a differential equation is. You really don't need to be an expert because the computer does all the heavy lifting for you, but it's important to know the terms when they come up, unless you're doing some advanced programming on the actual models themselves. And data wrangling and cleaning. I would say this might be the biggest one in here, is you have to start getting a grip on how to clean up your data. There's a saying is, bad data in, bad data out. Good data in, you're more likely to have good data out. Some applications of machine learning. Instance segmentation. Object detection, instance segmentation. You can see here where they use machine learning to go in there and find where the different cats are and the different objects are in the picture. And then in segmentation, it actually cuts them out. Kind of a fun one, especially if you have a Google Pixel phone and you can do little animation objects on top of your ongoing pictures you're taking or movies. Number plate detection. You can see here where we have a car and it comes in there and it finds a number plate on the car. Once it's done that, it can then do automatic translation. Automatic translation is we pick up some symbols, in this case on a machine, and it does machine translation so that you can know what it's saying even if you don't speak that language. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example, let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Now that you've seen the difference between numerical and categorical data, let's take a look at some different machine learning definitions. When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model. And that's why it'd be multiple linear regression. And finally we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where a regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today? Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is the statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle, a good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half you can see where we've broken that down into pieces, and as it goes through the first 2 points it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum is equal to 15, the sum is equal to 20, all the way up to x times y where the sum equals 66. This all comes from our formula for calculating a straight line where y equals the slope times x plus the coefficient c. So we go down below and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute and where that information comes from. It's called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part if you read through the brackets you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66, and take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1 plus 2.2 equals 2.8, so on and so on. And here the blue points represent the actual y values, and the brown points represent the predicted y values based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2 so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. We're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplotlibary and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlibary inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row. That's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it since it is a comma separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any 2 of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the 3rd row. And in there, we're going to take the label coder, and we're going to fit and transform the x, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally, we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the x and we go ahead and do that equal to one hot encoder fit transform x to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print x and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have x equals x colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now, whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise, we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit, because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to just put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn.linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom when we were doing all this summization? And then we also looked at setting it up with the different lines. And then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do x train and y train because we're using the training data, x being the data in and y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy x equals true fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a y_predict variable, and we're going to put in the x_test. And let's see what that looks like. Scroll up a little bit, paste that in here, predicting the test set results. So here we have y_predict equals regressor.predict, x_test going in, and this gives us y_predict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print y_predict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print y_predict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. We can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103,009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works and understand how good it works. So, calculating the R² value, that's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R² value. And we're looking at the error. So, in the R2 score, we take our y_test versus our y_predict. Y_test is the actual values we're testing. That was the one that was given to us that we know are true. The y_predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R² value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression.
What is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis. X is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the class, the outcome rather. So for a logistic regression curve, a threshold has to be set saying that because this is a probability calculation. Remember, this is a probability calculation and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0 and any value above 0.5 is considered to be 1. So an output of let's say 0.8 will mean that the car will break down. So that is considered as an output of 1, and let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now let's do a quick comparison between logistic regression and linear regression because they both have the term regression in them, so that can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information so that when a new employee's information is fed based on the rating, it will determine what should be the hike. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this where you're trying to find continuous values is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion and this is the ratings for which people did not get promotion, that is a no, and this is the rating for which people got promotion. We just plotted the data about whether an employee has got promotion or not, yes, no, right? So there is nothing in between, and what is the employee's rating, okay? And ratings can be continuous, that is not an issue. But the output is discrete in this case, whether employee got promotion, yes, no. Okay, so if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right because it looks like there will be a lot of errors. Thus, root mean square error, if you remember for linear regression, would be very, very high. And also, the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. it's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93, 94%, because the diagonals should have the maximum numbers. and the others other than diagonals, the cells other than the diagonals should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0 and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and one has been predicted as number 8 and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's just of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, yeah, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, all right, so with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test so that the training data set is used to train the system. So we pass this probably multiple times and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of the entire data is used for testing and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2, so that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x_train, y_train is for the training data set, x_test, y_test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x_train, the shape is 1383 by 64, and y_train has 1383 because there is nothing like the second part is not required here. And then x_test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method and we pass this particular image, and we see that the shape is or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes 2 parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that, the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less, and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0. So the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9, and this is the image of 1, and again this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as the condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need is I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. We have to make a couple changes as we go through this first part of the import. The first thing we bring in is numpy as np. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the NumPy come in for your numbers. It's called NumPython. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balance data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data.values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in where we're going to train it, and we have to know the answer to train it with. And then we have X test where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And that's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict en to print it. I could just as easily have put the print and put brackets around yPredict en to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test. That's the one we ran the predict on. And then we put in our yPredict en. That's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. So why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy. Runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where why random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area, and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. We have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes a decision is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree. But let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, and we're going to create a data set 1 and a data set 2. We just split it in two. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to two lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second two, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has two or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out, how does a decision tree work? So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, they're very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle, and it's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. In this example, last week, my son and I visited a fruit shop. Dad, is that an apple or a strawberry? So the question comes up, what fruit did I just pick up from the fruit stand? After a couple of seconds, you could figure out that it was a strawberry. So let's take this model a step further, and why not build a model which can predict an unknown data? And in this, we're going to be looking at some sweet strawberries or crispy apples. We want it to be able to label those two and decide what the fruit is. And we do that by having data already put in. So we already have a bunch of strawberries, we know are strawberries, and they're already labeled as such. We already have a bunch of apples, we know are apples and are labeled as such. Then once we train our model, that model then can be given the new data, and the new data is this image. In this case, you can see a question mark on it, and it comes through and goes, it's a strawberry. In this case, we're using the support vector machine model. SVM is a supervised learning method that looks at data and sorts it into one of 2 categories. And in this case, we're sorting the strawberry into the strawberry side. At this point, you should be asking the question, how does the prediction work? Before we dig into an example with numbers, let's apply this to our fruit scenario. We have our support vector machine. We've taken it and we've taken a labeled sample of data, strawberries and apples, and we draw a line down the middle between the 2 groups. This split now allows us to take new data, in this case an apple and a strawberry, and place them in the appropriate group based on which side of the line they fall in. And that way we can predict the unknown. As colorful and tasty as the fruit example is, let's take a look at another example with some numbers involved, and we can take a closer look at how the math works. In this example, we're going to be classifying men and women, and we're going to start with a set of people with a different height and a different weight. And to make this work, we'll have to have a sample data set of female, where we have their height and weight, 174, 65, 174, 88, and so on. And we'll need a sample data set of the male. They have a height 179, 90, 180 to 80, and so on. Let's go ahead and put this on a graph so we have a nice visual. So you can see here we have 2 groups based on the height versus the weight. And on the left side, we're going to have the women. On the right side, we're going to have the men. Now, if we're going to create a classifier, let's add a new data point and figure out if it's male or female. So before we can do that, we need to split our data first. We can split our data by choosing any of these lines. In this case, we draw in 2 lines through the data in the middle that separates the men from the women. But to predict the gender of a new data point, we should split the data in the best possible way. And we say the best possible way because this line has a maximum space that separates the 2 classes. Here you can see there's a clear split between the 2 different classes, and in this one there's not so much a clear split. This doesn't have the maximum space that separates the 2. That is why this line best splits the data. We don't want to just do this by eyeballing it. And before we go further, we need to add some technical terms to this. We can also say that the distance between the points in the line should be as far as possible. In technical terms, we can say the distance between the support vector and the hyperplane should be as far as possible. And this is where the support vectors are the extreme points in the data set. And if you look at this data set, they have circled 2 points which seem to be right on the outskirts of the women and one on the outskirts of the men. And hyperplane has a maximum distance to the support vectors of any class. Now you'll see the line down the middle, and we call this the hyperplane because when you're dealing with multiple dimensions, it's really not just a line but a plane of intersections. And you can see here where the support vectors have been drawn in dashed lines. The math behind this is very simple. We take d plus, the shortest distance to the closest positive point, which would be on the men's side, and d minus is the shortest distance to the closest negative point, which is on the women's side. The sum of d plus and d minus is called the distance margin, or the distance between the 2 support vectors that are shown in the dashed lines. And then, by finding the largest distance margin, we can get the optimal hyperplane. Once we've created an optimal hyperplane, we can easily see which side the new data fits in. And based on the hyperplane, we can say the new data point belongs to the male gender. Hopefully that's clear how that works on a visual level. As a data scientist, you should also be asking what happens if the hyperplane is not optimal. If we select a hyperplane having low margin, then there is a high chance of misclassification. This particular SVM model, the one we discussed so far, is also called or referred to as the LSVM. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have two sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a two-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a two-dimensional output. As you can see in this picture here, the 1D when transferred to a two-dimensional makes it very easy to draw a line between the two data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a two-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the two classes. We have our sample data set, and if you draw a line through, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a three-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high-dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data. Whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These three advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo and we have the young child going, "Dad, is that a group of crocodiles or alligators?" Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work, especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout and alligators have a wider snout. And of course, in the modern day and age, the father's sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the two groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here on the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice correction of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python notebook, or Anaconda Jupyter notebook with Python. We're using Python 3. I believe this is 3.5, but it should be work in any of your 3x versions. And you'd have to look at the sklearn and make sure if you're using a 2x version or an earlier version. Now let's go ahead and put our code in there. And one of the things I like about the Jupyter notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are numpy as np and matplotlibary.pyplot as plt. Now these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the numpy array. And I'll talk about that in a minute so you can understand why we want to use a numpy array versus the standard Python array. And normally it's pretty standard setup to use np for numpy. The matplot library is how we're going to view our data. So this has, you do need the np for the sklearn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm going to jump one ahead to line number 4. That's the sklearn.datasets.samples generator import make blobs. And I told you that we were going to make up data. And this is a tool that's in the sklearn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the sklearn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data. And we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have 2 numbers under X, and Y will be 0 or 1. That's the 2 different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual sklearn or the SVM is in 2 lines of code. And we see it right here with CLF equals svm.svc kernel equals linear, and I set SQL to 1. Although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. It'll be a nice linear line instead of a full plane. So we're not dealing with a huge amount of data. And then all we have to do is do clf.fit x, y. And that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done, is we've created 2 blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our 2 sets of data. One represents crocodiles and one represents alligators. And then we have our measurements. In this case we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon, comma, 0. That's from numpy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a numpy array. It turns out that our make blobs returns a numpy array. And this notation is great because what it means is the first part is the colon. It means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot and the second one is the Y plot. So the first one is on the bottom, 0, 2, 4, 6, 8, and 10. And then the second one, x of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dot, so we can see them instead of real tiny dots. And then CMAP equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using two colors, 0, 1, and that's why we get the nice blue and the two different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a third line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets, and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process one line at a time. And so in this case, I'm processing 2 lines. And then I'm just going to print, and you'll see clf.predict new data. So the clf and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4, is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it, and you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here, and I'm going to paste that code in. And you'll see that the plot show has moved down below. Let's scroll up a little bit. And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. We're going to fit the values on our SVM, and then we're going to plot scatter it, and then we're going to do a plot show. So you should be asking, why are we redoing the same code? Well, when you do the plot show, that blanks out what's in the plot. So once I've done this plot show, I have to reload that data. Now we could do this simply by removing it up here, rerunning it, and then coming down here, and then we wouldn't have to rerun these first 4 lines of code. Now in this, it doesn't matter too much, and you'll see the plot show is down here and then removed, right there on line 5. I'll go ahead and just delete that out of there, because we don't want to blank out our screen. We want to move on to the next setup. So we can go ahead and just skip the first 4 lines, because we did that before. And let's take a look at the AX equals plt.gca. Now right now, we're actually spending a lot of time just graphing. That's all we're doing here. Okay, so this is how we display a nice graph with our results and our data. AX is very standard used variable when you're talking about PLT, and it's just setting it to that axis, the last axis in the PLT. It can get very confusing if you're working with many different layers of data on the same graph, and this makes it very easy to reference the AX. So this reference is looking at the PLT that we created and we already mapped out our 2 blobs on. And then we want to know the limits. So we want to know how big the graph is. We can find out the x limit and the y limit simply with the get x limit and get y limit commands, which is part of our matplot library. And then we're going to create a grid. And you'll see down here we've set the variable xx equal to np.linespace, x limit 0, x limit 1, 30. And we've done the same thing for the y space. And then we're going to go in here and we create a mesh grid. And this is a numpy command. So we're back to our numbers Python. Let's go through what these NumPy commands mean with the line space and the mesh grid. We've taken xx, small s xx equals np line space, and we have our x limit 0 and our x limit 1, and we're going to create 30 points on it. And we're going to do the same thing for the y-axis. Now, this has nothing to do with our evaluation. It's all we're doing is we're creating a grid of data. And so we're creating a set of points between 0 and the x limit. We're creating 30 points, and the same thing with the y. And then the mesh grid loops those all together, so it forms a nice grid. So if we were going to do this, say, between the limit 0 and 10 and do 10 points, we would have a 0, 0, 1, 1, 0, 1, 0, 2, 0, 3, 0, 4 to 10, and so on. You can just imagine a point at each corner of one of those boxes. And the mesh grid combines them all, so we take the YY and the XX we created and creates the full grid. And we've set that grid into the YY coordinates and the XX coordinates. Now remember, when we're working with NumPy and Python, we like to separate those. We like to have, instead of it being x comma 1, x comma y, and then x2 comma y2, and in the next set of data it would be a column of x's and a column of y's. And that's what we have here, is we have a column of y's, and we put it as a capital YY, and a column of x's, capital XX, with all those different points being listed. And finally we get down to the NumPy VStack. Just as we created those in the mesh grid, we're now going to put them all into one array, XY array. Now that we've created the stack of data points, we're going to do something interesting here. We're going to create a value z, and the z equals the CLF. That's our support vector machine we created, and we've already trained. And we have a dot decision function, and we're going to put the xy in there. So here we have all this data. We're going to put that xy in there, that data, and we're going to reshape it. And you'll see that we have the xx.shape in here. This literally takes the xx, resets it up, connected to the y, and the z value lets us know whether it is the left-hand side. It's going to generate 3 different values, the z value does, and it'll tell us whether that data is a support vector to the left, the hyperplane in the middle, or the support vector to the right. So it generates 3 different values for each of those points. And those points have been reshaped so that they're right on a line, on those 3 different lines. So we've set all of our data up. We've labeled it to 3 different areas, and we've reshaped it. And we've just taken 30 points in each direction. If you do the math, you have 30 times 30, so that's 900 points of data. And we separated it between the 3 lines and reshaped it to fit those 3 lines. We can then go back to our matplot library, where we've created the AX, and we're going to create a contour. And you'll see here where we have contour, capital XX, capital YY. These have been reshaped to fit those lines. Z is the labels. So now we have the 3 different points with the labels in there, and we can set the colors equals K. And I told you we had 3 different labels, but we have 3 levels of data. The alpha is just makes it kind of see-through, so it's only 0.5 of the value in there. So when we graph it, the data will show up from behind it, wherever the lines go. And finally, the line styles. This is where we set the 2 support vectors to be dash dash lines, and then a single one is just a straight line. That's what all of that setup does. And then finally, we take our ax.scatter. We're going to go ahead and plot the support vectors, but we've programmed it in there so that they look nice, like the dash dash line and the dash line on that grid. And you can see here, when we do the CLF dot support vectors, we are looking at column 0 and column 1. And then again, we have the S equals 100, so we're going to make them larger. And the line width equals 1, face colors equals none. Let's take a look and see what that looks like when we show it. And you can see when we get down to our end result, it creates a really nice graph. We have our 2 support vectors in dashed lines, and they have the near data. So you can see those 2 points, or in this case the 4 points, where those lines nicely cleave the data. And then you have your hyperplane down the middle, which is as far from the 2 different points as possible, creating the maximum distance. So you can see that we have our nice output for the size of the body and the width of the snout, and we've easily separated the 2 groups of crocodile and alligator. Congratulations! You've done it. We've made it. Of course, these are pretend data for our crocodiles and alligators, but this hands-on example will help you to encounter any support vector machine projects in the future. And you can see how easy they are to set up and look at in depth. We're going to cover the K nearest neighbors, a lot referred to as KNN. And KNN is really a fundamental place to start in the machine learning. It's the basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor K? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, the use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those two characteristics. Now tell me if it is a cat or a dog. An odd question, usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or is not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning and is important for better accuracy. So at K equals 3, we can classify, we have a question mark in the middle, as either a square or not. Is it a square or is it, in this case, a triangle? And so if we set K equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put K equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the K changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of K? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right K? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of K, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your K is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing K, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your k value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the k value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise-free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where you might get into a gig of data if it's really clean, it doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57,170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine machine learning packages. But for very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. At 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up